Hello everyone, welcome back to the channel. I hope you're enjoying the series. In this video lecture, we're going to be solving this problem, shortest path in a grid with obstacle elimination. So in this problem, we are given a integer matrix of dimensions m cross n. That means we have a matrix grid of m rows and n columns which contains integers where each cell is either empty. If a cell contains 0, that means it is an empty cell, or 1. If it contains 1, that means there is an obstacle in that cell. From a given cell, we can move up, down, left or right if the cell on which we are landing is empty, and that is counted as one step. In this problem, we start from the top left corner and we want to reach the lower right corner, and to do so we have to take a minimum number of steps and we have to return that integer number, which gives me the minimum number of steps to reach from the source cell to the target cell. Also, we are given a constraint that along the way we can remove at most k obstacles where k is an integer. If it is not possible to find such a path, then we return -1. Let's understand the input and output format. In this problem, we will be given a grid of dimensions m cross n containing integers either 0 or 1 and an integer k representing the maximum number of obstacles that we can remove. And in the output, we have to return an integer representing the minimum number of steps to reach the target cell starting from the source cell. Let's see the constraints of the problem. In the constraints, m represents the number of rows in the matrix and represents the number of columns in the matrix, while the dimensions of the matrix can go up to 40 multiplied by 40. That means the largest matrix that we can have is of dimensions 40 cross 40, and the grid contains either 0 or 1. Let's better understand the problem statement using an example. So here we have an example. We have a matrix of dimensions 3 cross 3 which contain obstacles in 3 cells, while we have k as 1. That means along the path which we find to reach our target cell, we can remove at most one obstacle. So these obstacles are represented by 1, while 0 represents an empty cell. So we start from here, and one of the paths to reach the target cell is this. In this path, we take 4 steps. Another path that we can take is, and in this path we take 4 steps. Since we can remove at most one obstacle, in the second path we have to remove this obstacle to reach the destination cell, while other paths like this one contains 2 obstacles, one here and another here, while we cannot remove 2 obstacles along the way. Hence, we have these 2 possible paths which we can take to reach our destination cell. Therefore, the answer for this problem is 4. Notice that in these paths, we make only 2 moves. One move is towards right and another move is towards down. But there can be some cases where we have to move in all the 4 directions. There can be some optimal paths as well in which we have to move in all the 4 directions because of this constraint of obstacle. Fine. So let's see how we can solve this problem. So this is the same example represented in the form of a grid or matrix. This can be represented in the form of a graph, an unweighted, undirected graph where each node represents each cell of the matrix, while an edge in this graph connects 2 adjacent cells of the matrix. For instance, 0 0 is connected to 0 1 and 1 0. Here you can see that 0 0 cell is connected to cell 0 1 and 1 0. So these adjacent cells are connected by edges here, and the weight of these edges is 1 because to move from one cell to another we have to take one step. Fine. This matrix is represented in the form of unweighted undirected graph. in this graph we want to reach this cell. This is the target cell while this is the source cell. So we start from this cell and we reach this cell, and we want to find the most optimal path which takes least number of steps after removing at most k obstacles. Now this problem reduces to single source shortest path problem with unweighted edges, and we know to solve that problem we use BFS, but we have to modify our BFS a little bit here because of the constraints of obstacles. Fine. So in the BFS we explore all the paths, and whenever we find our target vertex, then the path through which the target vertex has been reached is the shortest path. Fine, that's the strategy of BFS. So let's see some points why BFS can be used to solve this problem. We know that BFS is used as a single source shortest path algorithm for unweighted graph, and it is used to find the minimum number of edges to reach a target vertex. So the minimum number of edges in this graph represents the minimum number of steps in this matrix. Therefore, that's why we use BFS here. Let's see the algorithm to solve this problem. So here we are given this matrix. This is the grid in which we want to find the optimal path from top left cell to bottom right cell, and for that we use a queue. So this is a queue. It contains first cell, that is top left cell initially. So this pair represents the coordinates of the cell, and this pair, in this pair the first integer represents the number of steps that has been taken to reach the particular cell, and k represents the number of obstacles that we can remove, or we can say that this is the current capacity that we have at this position. Fine. So standing at this cell, I can say I can still remove k obstacles to reach my target cell. Fine. So initially we push these variables in our queue, then we start our BFS search. So initially we pop this element out. Fine. So from this cell 0 0 we can move to these adjacent cells, and we can see that 0 1 represents this cell while 1 0 represents this cell. This cell does not contain any obstacles, so we push this cell as it is. So the coordinates or the variables for this cell would be, so these will be the variables or coordinates for the cell 0 1. So the number of steps that we have taken to reach this cell are 1, and we can still remove one obstacle to reach the target cell. We push 1 along with the steps, while to reach cell 1 0, which contains one obstacle, the coordinates would be, so here you can see that we have taken one step while we have also removed one obstacle in this cell. Therefore, to reach the target cell we do not have any obstacle. Therefore, to reach the target cell we cannot remove any extra obstacle that come along the way. Fine. Then now we pop the least reset element from the queue, which is this element. Hence we move to cell 0 1, which is this cell, and from this cell we can move to cell 0 2 or to cell 1 1. Although cell 1 1 contains an obstacle, but we can remove one obstacle as we have the stamina to do so. Therefore, we can move to two cells from this cell. One of the cells is 1 1 and another cell is 0 2, and we remove this element from the queue. So we push this cell into the queue. So we push this cell 1 1 into our queue, and then we can also move to cell 0 2 while not removing any obstacle because this cell does not contain one. So we push this cell as well. Here you see that to reach cell 1 1 we require 2 operations, and to reach cell 0 2 we require 2 operations, and we do not have to remove any obstacle to reach this cell because along this path we do not have any obstacle. Therefore we put 1 as it is. Then we pop the least recent item from the queue, which is cell 10, that is this cell, and you can see that from this cell we can move to cell number 20, while cell number 11 is already visited. So we marked it as visited. So we took a visited array or a hash map where we are marking the cells which we are pushing inside this queue as visited, so that we do not have to visit them again. Fine. So from 10 we visit cell 20, while the number of steps increases by 1 and the obstacle removed stays the same. So we pop this element out of the queue and we push the cell 20 inside the queue. And here you can see that we are using two operations to reach this cell, while we removed one obstacle to reach this cell. Then we remove the least recent cell. That cell is 11, that is this one, and from this cell we can move to 4 directions: left, right, up and down, while in this case the cell which is just above this cell, that is 01, and which is left to it, that is 10, are already visited. So we visit these two cells, 12 and 21, while we do not have to remove any obstacles to reach those cells. So we pop this element out and we push the cells in the queue. So here to reach these cells, that is 1, 2 and 2, 1, we require 3 operations, and we removed one obstacle to reach these cells. Notice that there can be some cases where there are 2 paths or more than 2 paths to reach a particular cell ij, and the steps to reach that cell can also be same, let's say s. Then out of all those paths we would choose that path which removes minimum number of obstacles. Then we remove the least recent element from the queue, that is 02, this cell, and we can move from this cell to the cell 12. So we push cell 1 in the queue. In this way we keep removing elements from the queue and keep pushing the adjacent elements if they can be visited. So finally we would have our cell. So using this strategy we would keep pushing the elements inside the queue and popping and running our BFS till the target cell is reached. We can see that in this matrix we can have more than one optimal paths to reach the target cell. One of the paths is just move down and then move right. Another is move right and then move downwards. So which one to choose? We can see that in this path we have to remove one obstacle, while in this path we do not have to remove any obstacle. So if there are more than one paths to reach the target destination or some cell ij in the matrix, then with same number of steps, we can see that the number of steps along these paths are same. Then in this case we choose the path which removes minimum number of obstacles or which contains minimum number of obstacles, so that at any cell ij we have maximum remaining capacity to remove obstacles in the path to reach the destination cell. So we have to optimize this variable as well, that means this one, because we can reach the target cell along many paths and we would choose the path which removes minimum number of obstacles. Fine. So that's another variable which we have to consider in this case. So let's see the implementation for this problem. So to handle that, to optimize the number of obstacles removed, we use an array, lives array. We use lives array where lives ij represents the maximum lives that we can have to reach a particular cell j. Here lives represents the capacity to remove at any cell ij. We want to maximize this lives. We want to maximize these lives while keeping the steps minimum. Fine. So this is the function shortest path function which takes in the grid and the capacity to remove obstacles or lives. So we calculate the dimensions of the grid. Then this is the direction vector which is used to move in 4 directions. This is the Q that we are initializing. Initially we are pushing the first cell, that is top left cell, along with the obstacle removing capacity or lives. We have K lives initially. Initially the number of steps taken to reach source cell are 0, and we initialize lives array with -1. Fine. Why do we do this? Because if we find a cell in the queue such that to reach that cell we have more number of lives than we have in the lives array, then we're gonna update the lives array there. So here we run our BFS search, we calculate the size of the queue, then we iterate till the size of the queue, and we extract our cell from the queue and the current lives that we have to reach this cell. Then we check if the cell that we are removing from the queue is the target cell. If it is the case, then we return the number of steps right from here. Otherwise, we check if this cell contains an obstacle. If it contains an obstacle, then we have to remove it. So we decrement our current lives variable by 1 because we are using 1 life here to remove that obstacle. After that, we move to the 4 directions, namely left, right, up and down. And for each of these adjacent cells, we check if these cells are valid. That means they lie inside the boundary of the matrix. And here we are checking the condition for the lives. If the current lives that we are having at the current cell are greater than the lives which are present in this lives array, or it simply states that if we take the path that we are currently taking, then we would have current lives remaining, and if along this path the lives remaining are greater than the lives that this array stores, then that means this path is more optimal than the path for which this lives stores the current lives. Therefore, we update our lives array and we push the new cell into the queue. Then we increment the number of steps that we are taking, because at each, if we are not returning from here, then that means we are taking at least 1 step. And after quitting this while loop, if we do not find the target vertex, that means there is no way we can reach the target cell using the given test input, so we return -1 from here. Fine. I hope you understood what we are doing here. Then so let's discuss the time and space complexity for this implementation. So you can see that the time complexity for the problem is n cross m, because we are visiting all the cells of the matrix while performing our BFS, and there are n cross m cells in the matrix, while the space complexity is also n cross m, because in the queue, because we are using this lives array and because of the queue that we are using, the overall space complexity becomes n cross m. Fine. So let's see the implementation. So this is the shortest path function which takes in the grid and the lives. First we calculate the dimensions of the grid. Then this represents the direction vector which is used to navigate to the adjacent cells. Then we declare the number of steps which will store the final answer. Then we declare our lives array, which is used to optimize the lives k. Then we declare our queue to perform our BFS. Then we push the source cell into the queue. Then we perform our BFS search. So in this while loop, we are calculating the size of the queue. We are iterating over all the elements of the queue. Then for each element, we are moving to the adjacent cells if it is possible to move. And here we are checking if the grid contains an obstacle. Then we decrement the current lives that we have. And here we are returning the number of steps if we find our target cell. Then here we are moving to all the adjacent cells of the current cell, and if it is possible to move any of them and we have a better path which is checked here, then we push that cell into the queue and we update our lives array. So the purpose of this lives array is to optimize our current lives, or to reach any cell ij we want to minimize the number of obstacle removals. Fine. And then we increment our number of steps that we have taken to reach. And finally, if we do not find our target cell while performing the BFS here, then that means there's no way we can reach the target cell. Therefore, we return -1 from here. So this is the implementation in C++. Let's see the implementation in other languages. So this is the implementation in Java, and this is the implementation in Python language. Like the video, then do like it and make sure to subscribe to my YouTube channel. I will see you in the next video. Till then, take care. Bye bye.